Hey, North, Mr. Yergler here. We've talked a little bit about polyprotic acids, but there's a few more things that I want to go over, and this will kind of help you with some of the things that you'll come across in the worksheet. So first, just a couple bullet points that just to kind of make sure that everyone's on the same page. Polyprotic acids are the ones that have more than one H. So H2SO4, H3PO4, phosphoric acid, anything that has two or more H's on the front of the molecule is going to be a polyprotic acid. And each of those H's come off one at a time. Each ionization has its own equilibrium. And because each has its own equilibrium, they all each have their own Ka. The first dissociation has the greatest effect on the pH. Usually the second and maybe third, if it's there, H's have only a very slight, because their Ka is so small, it just barely contributes to the pH. So little that it's hardly even measurable. We kind of ignore it in a lot of cases. The reason for that is because as the protons come off, the anion gets more and more negative, and so it kind of holds on to that proton more and more strongly. Here's an example of H3PO4. So this shows that each H comes off one at a time. So it goes from H3 to H2 PO4-, and then to HPO4-2, and then to finally PO4-3. So this is a triprotic acid. So a lot of times you'll see the Ka's kind of listed as Ka1, Ka2, and that's for each individual H plus that comes off. Okay. Now H2SO4 is the only acid that is a strong acid with its first proton, and the second proton is weak, but it's strong enough that it actually makes a difference. You can see here it's times 10 to the negative second. That's not quite so small that it's negligible. The reason we know that this happens, as you titrate a polyprotic acid, it has two curves, or it has a curve for each proton. So there's multiple equivalence points, and so you can actually identify from the titration curve how many protons there were on the acid. All right, so we'll go through one calculation example. This is kind of more complex than you'll probably see on an AP exam or something like that. But I kind of want to show you how you can go through this, because it kind of helps you to wrap your head around what's going on in the solution. So we have H2C2O4 oxalic acid, and we have a first Ka and a second Ka. Find the concentration of each of the species if we're starting with 1.5 molar. So the first dissociation, it's helpful to go ahead and write that out. We don't really need to do an ice table, but you could. We can just jump to the K expression, which is our Ka, our first Ka, with this first dissociation reaction, products over reactants. Now this is going to be equal to x squared over 1.5. Now you could neglect x here. The Ka is not really that small. It is going to make a difference, but I'm going to go ahead and neglect it so that it just kind of makes it a little cleaner and easier to kind of work through the math. If you don't neglect x, it changes the final answer by 0.03 roughly, so it doesn't make a huge difference. So now we know that the x, which is the H plus concentration for that first dissociation, and the HC2O4- concentration is 0.3 essentially. So the H2C2O4 concentration has decreased by 0.3 essentially. So it's not really any longer 1.5, it's actually 1.2. Now let's write our second dissociation. So here's our second dissociation, which is starting with the product from the first one and then breaking off one more H plus. Now we can go ahead and write our K expression. Notice the only change is the species that we have in there, because we have a slightly different equation. Now it's important at this point to kind of stop for a second. The H plus concentration we don't know. We also don't know the C2O4-2 concentration. And it seems like we don't know the bottom, the denominator of this either. But let's keep in mind where this is coming from. This is coming from up here, where we just figured out what x was. It was 0.3 essentially, right? So that concentration in the denominator there is the same thing, and so we can go ahead and plug that in. I'm going to switch variables to kind of keep them separate so that it's a little bit less confusing. And when you solve for y, here we can neglect the variable. It's a lot easier to neglect the variable because the Ka is so much smaller. So now we have the C2O4-2 concentration, which is 4.36 times 10 to the negative third. So to find each concentration, remember this is kind of a key idea here, is that the H plus is mostly from the first dissociation, but there is some added H plus from the second dissociation. So you would need to add those up. ends up being 0.301 molar. And then our X is our 0.297 from the first dissociation, and then the final dissociation is the value of Y, which is the 4.36 times 10 to the negative third. Alright, so that's about as complicated as the calculations get. It's going to be more about kind of qualitatively understanding how the titration curves look on polyprotic acids, and kind of like what, based on the KAs, what species is going to be predominant, more than just actually just calculating a ton of concentrations. So if you have any questions on this, be sure to write those down and bring them up in class. This is Mr. Yergler signing out.